We really have an exciting talk today from Dr. Filiberto talking about volcanism on Venus and what we know about it. Before we get going, I just want to welcome everybody to this week's rendition of the DeFord Lecture Series. As most of you know, the DeFord Lecture Series used to be called Technical Sessions, and it's been a tradition in the department here at the Jackson School since the late 1940s. It started out as the official venue for disseminating Department of Geological Science graduate student research, faculty research, and it's grown into this lecture series where we have distinguished guests such as Dr. Filiberto presenting their research to members of our community. It's named the DeFord series after Ronald Kennison DeFord, who was a faculty member here in the department for many years. He joined the university in 1948 and served as a graduate advisor in the department from 1949 to 1967. He supervised 19 PhD dissertations and 126 master's theses. And one of his enduring contributions was teaching. In addition to teaching, was leading what was at the time called Technical Sessions. And so in his honor, we've renamed this the DeFord Lecture Series with the mission to present cutting edge research from around the world to members of the Jackson School, and now in this virtual age to the broader community. So welcome everybody. With that, I'm not going to take any more of your time. I'm going to hand over to Chen Sun, who will announce today's speaker, introduce us to today's speaker.
Thank you, John. Good afternoon, everyone. It is a great pleasure for me to introduce our DeFord lecturer today, Dr. Justin Filiberto. Dr. Filiberto is a senior staff scientist at the Lunar and Planetary Institute. He received a bachelor degree from University of Miami and a PhD from Stony Brook University. He then did postdoc research at the Lunar and Planetary Institute and Rice University. After 7 years at Southern Illinois University as a professor, he moved back to the Lunar and Planetary Institute as the senior staff scientist in 2018. Next week, Dr. Filiberto will start his new leadership role at NASA's Johnson Space Center as the branch chief in Actual Material Research Office. Today, Dr. Filiberto will be talking about volcanism on Venus, but beyond Venus, he has also been working on other planetary bodies, Mars, Earth, and the Moon. His research uses experimental petrology, mineralogy, spectroscopy, astrobiology, and geochemistry. He is particularly interested in planetary volatile budgets, habitability, and magma genesis. He is a member of the Da Vinci mission team, which was recently selected by NASA for its discovery program and will be the first US-led mission to Venus' atmosphere since 1978. Everybody, please join me in welcoming Dr. Justin Filiberto. Welcome, Justin. It's all yours.
Thank you for the invitation and the opportunity to talk to you about Venus. So today I'm going to be talking about evidence for present-day volcanism on Venus and some experiments we've been doing to constrain the age of lava flows. And this is a nice cartoon. We're talking about this one. We all logged in. This is from ESA, but it gets used routinely by the press when we're talking about the age of volcanoes on Venus. And what a Venus volcano will look like. And while this is very catastrophic and very intriguing, it is probably not what Venus volcanoes look like or what volcanism looks like. And so we'll go through that. Okay, so to start with, I actually like to just take a sort of step back to talk about what information we have about Venus, what missions we've had, and where we're going. And one of the things I always like to point out is how few missions we've had to Venus. And obviously this is going to change, but this is the list of successful missions to Venus. And today on Mars, we have almost this number of active missions on Mars today. So it's kind of incredible just comparing the two bodies, especially I work on both. The grayed out missions are missions that flew by and got images, got spectroscopy. The three in the middle, the Venera and Vega probes, actually were orbiters and probe missions. The Venera and Vega data went into this, went through the atmosphere. They landed with this giant lander here. analyzing rock chemistry, analyzing atmosphere. The longest lived one lived just over an hour. So again, compare this to our decade or longer than decade-long Martian rover. This is the issue we have with Venus. And then here, where we have a lot of data from NASA, Pioneer Venus, and Magellan back through the 70s and into the 90s, we've had orbiters around Venus. And then in the 2000s, European Space Agency sent Venus Express into orbit, and I'll actually show quite a bit of this data later in the talk, which ties to the lava flows. And then our Japanese colleagues, Jaxus and Akatsuki, back in 2010, this is an atmospheric mission that studied sort of the weather and from the cloud deck up, and I'm not going to really talk too much about this. As Chen talked about, and as I've alluded to, we do have new missions going to Venus, and so life is going to change. We're going to get a whole lot more data at the end of this decade and into the next decade. NASA is sending 2 different missions. Veritas, shown here, is an orbiter that's going to go around Venus. It has a radar, it has a spectrometer, so we will get information about the surface of Venus, both from radar imaging as well as spectroscopy. The mission I'm a co-on, Da Vinci, shown here in cartoon, is an atmospheric probe. We'll be dropped off, we'll come through the atmosphere. We're going to measure the chemistry of the atmosphere, and importantly, this really, really thick cloud deck. We'll measure the chemistry of the cloud deck as we come through, including things like noble gases, sulfur. If anyone heard about the phosphine or possible phosphine detection last year, we'll look for phosphine. And then the portion of the mission that I'm attached to is once we get below the cloud deck, we're going to drop off our shields here and actually image the surface of Venus below the cloud deck, which means we don't have to do cloud subtraction, and get images of the Venus as we come down in nested images all the way to the surface, sending all of this data back before we make our hard landing. And then the final of the 3 missions in 2032, our European colleagues will send the Envision mission. This is an orbiter mission. It also has multiple radars, spectrometer similar to Veritas, and we'll have a huge amount of data coming back from Venus in the 2030s. So stay tuned for all of that. So one of the things I've been focusing on is where are we before this fleet of mission arrives? What are the big questions? What are the open sort of debates within Venus? And the ones that I'm going to focus on in this talk are the ones that are in black. The other ones are in gray, are really interesting questions that will be addressed by these missions, but I'm not going to cover here. So what is the timing of volcanic activity on Venus? Has it been gradual? Has it been more catastrophic, where it comes out like large igneous provinces where we've got a huge outpouring of basalt and then things get quiet? Or is it more gradual, like a ocean island, where we just have constant or near constant volcanism coming out? Is it volcanically active today? Are these volcanoes still active? Are they active in the recent geologic past? Or is it like the moon, where it cut off a lot earlier in its history? And then something else has been a focus of my career, as Chen pointed out, is what is the volatile content of these basalts? Were they hydrated? Did they have lots of chlorine like Mars? Did they have more water like the Earth? Or are they rather volatile, depleted like the Moon? That's a very large question. 2 large picture questions that, as I said, will be talked about, will be addressed by the missions, but not going to go into here. Are the Venus clouds habitable? The surface of Venus is 470 degrees, so it is beyond what we know about habitability of a planetary surface, but the clouds are ever present. They are a lot cooler, they have nutrients, so are they a habitable environment? And if they are a habitable environment, are they inhabited? Something that we'll be able to at least look into. Another question, what are tessera terrain? These, and I'll show you a picture, at least on the topography map. These are ancient cratons. This is 4 billion-year-old rock on Venus that we don't quite know what they are. They could be ancient granitic cratons like the Earth. They could be altered basalts and sediments, more like Mars. This is a first order question that's still being debated. You'll see how important this is. And just this is where DaVinci Plus is going to come down over a tesseract terrain and actually image this, so we'll be able to help constrain this. So I'm going to focus on this first one today. What is the timing of volcanic activity? First, I'll talk about what we know about, or what little we know about the petrology of Venus lavas from the chemical analysis from Venera and Vega. Use that to talk about, okay, what did these look like if they were on the Earth? Water content, CO2 content, and then go into the next questions of, is Venus volcanically active today, and what does that mean? So this is broken in two parts. First, focusing on the igneous rocks of Venus, the Venera and Vega analysis from our Russian colleagues, and then using, I'm a high pressure experimental petrologist, so using terrestrial experiments to constrain things like pressure, temperature of origin, and water content, possibly CO2 content of lava, at least sort of first order, where are we in terms of Venus lavas. And then going into the next, using orbital measurements of Venus lava flows to talk about what do we know, why we think they're young, but then using, again, experimental results to constrain how young is young and how old these lava flows are. So that's sort of the two aspects of this talk that I'm going to focus on. Since most of you don't probably know the history of Venus, I'm going to go through at least some of the background of Venus exploration, at least quickly. This is the Venera and Vega program from our Russian colleagues. You can see this is the giant lander here. This was the program, so there were orbiters, there were flybys, and then this came through the atmosphere. It was released through the atmosphere, it landed on the surface, and the longest lived of these was Venera 14, and it lasted for just over an hour. Some lasted shorter, some were down in the 20 and 30 minute range. This was the longest. So again, compared to when we send something to the moon, when we send something to Mars, they last for years, if not on Mars, over a decade. And this is what we're dealing with on Venus, where we've got a surface that's 470 degrees. We have an atmosphere that's CO2 rich with sulfur in it. So we've got a very caustic atmosphere, very hot surface. And the surface is also at 92 bars. And so we need our electronics to survive on the surface, high pressure, high temperature, and an acidic environment, which is very hard to do, especially for long periods of time. The Venera did send back, this is Venera 13, it sent back the first color photo of the Venus surface. You can see up here is the image sent back. You can see that hazy atmosphere here, making everything sort of yellowish. There's a color plate here and a white plate in the middle. And this was used to remove the atmospheric effects. And so you can see here is a color with the atmospheric effects removed. You can see these look like basaltic rocks, or at least black rocks. And you can see there is some reddish hue even with the atmosphere removed. And so these are probably still not fresh basaltic rocks, but have some amount of alteration. So chemically, this is from Alan Treeman's paper. This is uranium thorium, and you will see that the number of dots on each of my figures changes because every Venera and Vega probe carried different instruments. And so we have different chemical analysis for different rocks. Each of these represents one rock analyzed at one landing site as well. So this is uranium and thorium. This is chondritic abundance. You can see, at least within the huge error bars we have for the Venera and Vega landing data, Venus looks chondritic in terms of uranium thorium. It should be chondritic, so that's not a surprise. Potassium to thorium is shown here. Here's chondritic. Here's the Earth's mantle here. Here's 0.08 times chondrites. You can see that for most of the analysis, with the exception of one here, within error bars, they look like the Earth. And this is something we're going to see a lot with this data, is that Venus looks very Earth-like. Interestingly, Venera 9 looks different in terms of both uranium, thorium, and potassium and thorium. However, we don't have other data to back up why this is different. So this is one of the sort of unanswered questions about Venus. Again, this is from Alan's paper. This is calcium to aluminum over titanium to aluminum. So bulk rock, this is, again, now we only have 3 data points because we only have 3 mostly full chemical analysis. This is compared to other planetary rocks we have. So Martian meteorites are shown here. Eucrite basalts are basalts from, or thought to be from the asteroid 4 Vesta. They're plotted here. Rocks analyzed by Mars exploration rover Spirit at Gusev. So these are basalts are plotted in here. Lunar basalts, mid-ocean ridges are here, and Earth ocean islands and more alkalic rocks are here. And again, you can see, at least on first order, Venus basalts look sort of similar to the Earth. And so we can use the Earth as sort of our analog for figuring out what these rocks are. We can use the extensive experimental petrology on terrestrial rocks, making mid-ocean ridges, making different types of ocean island basalt to figure out sort of the bulk chemistry and what these 3 rocks can tell us about Venus. So what does this tell us? We can use the Earth as our baseline, which is good. We can assume Earth-like basaltic chemistry. There may be some differences, but at least on first order, Venus looks like the Earth. We can also then use Earth-like magmatic processes. You notice this figure, I'm using mid-ocean ridges and ocean islands. I don't have subduction zone rocks on here because there's nothing that looks like a subduction zone on Venus today. And so these are more akin to what we should see there. We can use our experimental crystallization studies to constrain formation conditions. So pressure, temperature of our magma chamber, how we're fractionally crystallizing things, water content of the magma, and then we can use that to even back out magma, water content of the interior. Sorry. So this is sort of what we can use. And again, we only have these 3 rocks. You can see the large error bars on all of these. So this is always going to be the issue when we study Venus. So the Earth is the model. This is total alkalized versus silica, a common way experimental petrologists classify rocks. These numbers represent rocks from different volcanoes on the Earth, where we have some idea based on experiments of what conditions the magma chamber was at, what conditions the volatile, pre-eruptive volatile content, so water, CO2, and we can use these as our background when we start applying things to Venus. One caveat to this is we do not have sodium analyzed for Venus rock. So instead of total alkalized versus silica, I'm going to simplify this to potassium, which we do have versus silica. The problem with this is anything in the middle here, these different types of rocks here, the difference in these is largely due to the sodium to potassium ratio, and that falls out when we're only looking at potassium. So we've got rocks from Thimuli here in Galapagos. So these are low pressure systems. We've got Hawaii, Ascension Island, Mandawar. So these are sort of hotspot continental volcanism style alkalic. And then these are silica undersaturated rocks of Tristan da Cunha. So for one example, you can see VNIR 14 and Vega 2 plot down here. The first thing you can see is silica is 50 plus or minus nearly 10. So huge error bars on our silica content. Within error, they look like a pholitic basalt. So something down here from any of these volcanoes though. Tristan da Cunha, it does still have that large error bar of 10, or sorry, VNIR 13 has the large error bar of almost 10% and has large uncertainty in potassium. But even with those large error bars, you can see that VNIR 13 is consistent with high alkali silica undersaturated basalts. And of course, there is uncertainty over exactly the type, but it does fit well, at least first order, with Tristan da Cunha. I'm only showing this one as an example. If you go to my 2014 paper, I went through every element that was analyzed in these. So we have everything but sodium. Magnesium is actually at sort of detection limit. But if you go through all of it, it does match with VNIR 13 being a silica undersaturated and VNIR 14 and Vega 2 being either mid-ocean ridge basalts or ocean island tholeiites, but sort of that typical basalt chemistry. And so if we use experimental results, and this is sort of a flavoring of the experiments I used to constrain these, of where the magma chamber was, where these formed. I'm going to highlight the Tristan da Cunha one because this is where we have sort of better constraints for Venus. These are high pressure origins, so these came from depth. On Earth, these are thought to have about 0.28% water in the magma itself, and so it would be an order of magnitude less than that in Mantle. So we're looking at some amount of water in the magma and in the interior. I have a star here because Rajdeep Dasgupta, my previous postdoc advisor and Chen's previous postdoc advisor, has spent a lot of time working on these and suggested that they also probably need large amounts of CO2 in the interior to produce these, at least on the Earth. And so I put that as a sort of caveat there. For the other two, they fit with any of these models, and so we really don't have constraints on how they form, but we do at least have one that suggests a deeper origin and some amount of water and possibly CO2 as well. We can also model sort of pressure and temperature formation conditions using silica activity in the rock and iron magnesium exchange geobarometry. And this is work from Sinti Lee with averaging for Venus. I took all three of those basalts and averaged into one. And this is from Sinti Lee, Matt Weller, and Megan Duncan, and Gregory Shellnut. This is for mid-ocean ridges. This is to compare to Hawaiian hotspots. This is Venus. I don't have error bars here. I do on the next slide, but it's a bit hotter and deeper than the mid-ocean ridge system. It's consistent with ocean islands, at least, again, first order. If we pull this out with error bars, and I wanted to do this separately for this reason, VNIR 13 and VNIR 14 here look, at least VNIR 13 is consistent with an OIB. VNIR 14 sort of splits right down between the two. Vega 2 is probably more altered than the other two, and depending on how you model this, it either looks very much like a morb or is much hotter than an ocean island basalt. And so I wouldn't put too much trust in either of these because I think Vega 2 is showing more alteration than the other two. But this does tell us that the interior of Venus is similar to, temperature-wise, similar to the Earth. There's evidence of sort of ocean island style magmatism. There's possibly suggestion of mid-ocean ridge style volcanism. We don't have ridges like we do in the mid-ocean ridge going all the way around Venus, so it would not be a complete morb, but it would be that style of volcanism. So just to summarize this before we talk about sort of next bigger picture of what type or how old is this volcanism, what other evidence do we have? Vega 2 and VNIR 14, they're consistent with a terrestrial basalt called an olivine tholeiite. Vega 2 may be more morb-like, but the error bars on Vega 2 are much larger. VNIR 14 looks kind of ocean island basalt-esque. Its mantle potential temperature, or TP, is sort of splits right between the two, so there's uncertainty there. And the issue here is we just have large error bars on our data from Venus. VNIR 13 is where we have better data with lower error bars. It is consistent with the silica undersaturated rock. Origin similar to rocks from Tristan da Cunha, deeper origin than Vega 2 and VNIR 14. Probably some amount of water in the basalt. I would say that's a first order guess, and I if we had better data, would be able to constrain it better. And there was probably a carbon-rich source region, but again, the exact amount of carbon at this point with the error bars we have is unknown. So that's petrologically what we know about Venus. But we have other data that we can use to constrain lava flows. We can use experiments to constrain them. And so I'm going to talk about these, and I'll talk about how some of my experiments play into this. We do have radar imaging of the surface. This is from Magellan, Pioneer, and even the Venera data from our Russian colleagues. Radar gives us an imaging of the surface, but radar is dependent on the bulk chemistry, the mineralogy, the texture of the rock, the grain size of the rock. And so it gives us more than just imaging in all of these pictures that I'm going to show. We also have some amount of spectroscopy, and the issue with Venus is this very, very thick cloud deck. Our spectrometers can't see through like we would when we go to the moon, when we go to Mars, and we get these nice squiggly lines. But Galileo, on its way to Jupiter, did turn on its NIMS, the near infrared mapping spectrometer, and look at Venus, and we do have spectroscopy from that of the northern hemisphere. The northern hemisphere. Venus Express was in orbit and had their Viridis instrument, visible and infrared thermal imaging spectrometer. And for both of these, we do have one channel right at the one micron region that can see down to the surface and back and get information. So I'll go through that as well. So from our radar, we can also derive topography. First thing you can notice, or at least first thing I always notice, is that we have swaths where we have no data. We have swaths where we have very low resolution data. This is not Mars, where we have global high resolution topography. However, with Veritas and Envision in the next decade, we will have much, much higher resolution topography going forward. So for topography, the white and red areas are the highlands. The blue area is not water. This is our plains or our lowlands areas. The red dots are where Venera 13, so the rock I was talking about, Venera 14, Venera 9, 10, Vega 1 and 2 are white, all landed on the surface. So you can see just in comparison. You can see this is what I was talking about in terms of large cratons. This is the areas that are thought to be 4 billion years old, or older than that, and telling us about the sort of early epoch in Venus's history. And we'll know a lot more about those once the fleet of missions arrives. So going into our radar and looking at our volcanoes specifically, I'm going to give a few examples. This is Sapas Mons. You can see the volcano here, our center. You can see all of these radiating out are lava flows. The brightness, as I said, reflects mineralogy, density, porosity, and grain size. But you can see lava flows coming out here. The bright lava flows over here are thought to be much younger. The brightness of the volcano at the top may be a change in mineralogy. So we're seeing different regions or different reasons for the brightness depending on where you are. Sapas Mons is 400 kilometers across. It's 1.5 kilometers across, or I'm sorry, tall. It is a very gentle slope, about 0.5 degrees. It has very long lava flows. You can see these pointing out here. This is similar in many regards to Hawaii. You can see our sort of lava toes, and you can see similar structures at the end of our lava flows here. I started this talk with a cartoon from ESA that's been used by the press, and I love to show this image of Mount Mons. This is one of my favorite volcanoes on Venus for a host of reasons. One being you can see this lava flow sort of coming at you here, and you can see again that sort of structure of lava toes where they're breaking out. The other reason I like to show this is this is a 20 times vertical exaggeration image. And if you look at this, you'd be like, wow, Venus looks like Cascadia. I would look at that and I would go, that looks a lot like Mount St. Helens before it obviously blew off its top, or Mount Rainier, and we've got evidence for subduction zones. However, this is 20 times exaggerated. And if we sort of squash this back down, this is what Sapas Mons actually looks like. It looks like, so instead of looking like a subduction zone volcano, it looks like Hawaii and a shield volcano. The other reason I like this image is Sapas Mons is another one of these volcanoes where this lava flow and some of the others are suggestive of unweathered lava flows, and so relatively young, and so my results can help constrain how old relatively young is for some of these volcanoes. So the question is, and the title of my talk, how old is volcanism on Venus? Has it been going through today? Did it cut off millions of years ago? Did it cut off billions of years ago? And to look at this, we're going to use what spectroscopy we do have. And this is from Venus Express. This is the Virtus instrument. So this is a near-infrared spectrometer. As I said, unlike Mars, unlike Venus, unlike Moon, unlike many planetary bodies where we can get a squiggly line, we can deconvolve it, we can talk about exactly what minerals are there and go from there. For Venus, we're looking at what channels can get through this very thick atmosphere and get back. And so we're only looking at a handful of channels that can do this. And so when we typically look at our spectroscopy, we're looking in the 1 micron region. Now, for someone who studies basalts, that's actually not a bad region to look at. 1 micron is where the iron silica body is. And so this is telling us a lot about iron oxidation state, whether iron is in olivine pyroxene or iron is in things like magnetite, hematite, or alteration phases. So instead of mapping sort of mineralogy, we map emissivity, again, at that 1 micron. And my equation disappeared, sorry. So emissivity is 1 minus reflectance. I think this is on a later slide. So a lot of people, when we think of Mars, we think of things in terms of reflectance. Reflectance would be down, sort of just flip your numbers over. So when we look at emissivity, most of Venus has sort of the same low emissivity down here. But when we look at Imdar Regio, there's a bright red spot here with very, very high emissivity. When we look at this, this is a volcano called Idan Mons. Mons meaning volcano. Idan's just the name of the volcano. And we've got high emissivity. Again, this is, if you're used to thinking reflectance, just flip. So this is low reflectance right in this area, right from sort of this flank right here in this lava flow. And this was back in 2010, back in 2010, Seuss McCarr published this paper saying there are lava flows on Venus that have low reflectance or high emissivity consistent with being unaltered or fresh lava flows on Venus. And back then they said, okay, based on what we know about Venus, these are young. They might be 2.5 million years old or younger. They might even be 250,000 years or younger. So how can we use emissivity? Again, we're looking at this 1 micron range. They're orbital measurements. They provide information about mineralogy, but we can't get all minerals like we would for other planetary bodies. Felsic and secondary minerals have a low emissivity. Mafic minerals or fresh lava has higher emissivity. So when we break this down, this is emissivity, and this is wavelength. And again, we're looking at 1 micron for most of this, so right in here. You can see that our rocks do actually nicely pull apart. We've got basalts up here, dacites and andesites, granites, and then quartz sands here. And this is data from Darby Dyer's work. The high temperature measurements were done in Jorn Halbert's lab, the DLR, and some measurements were done down here at Johnson Space Center on a paper we published earlier this year. So you can see we can use emissivity to pull out first order, basalts evolved things and altered things. And I will point out that if we look at basalts, hematite, so weathered basalt, and granodiorite, or felsic rocks, you can see as we alter our basalt, it is also going to move in the same direction of our felsic rocks. And so we have a hard time seeing the difference between felsic rocks and weathered basalts, especially when we're only looking at one micron. If we had more spectroscopy, which we will get with all 3 missions going forward, we'll have 6 channels from Veritas and Envision. We will have 4 channels from Da Vinci. We will be able to pull apart at least first order alteration versus felsic rocks. But from the Veritas, from the Vertis data. So coming back to this, these fresh lavas shown here at M. del Regio, and this is topography shown here. This is our emissivity. The lava flows here from Sue's paper are suggestive of fresh lava. And as I said, these are less than 2.5 million years old, or possibly less than 250,000 years old, based on alteration models of how quickly lava flows should alter on Venus. So how do we constrain this? And this is where my work comes in. Can we experimentally alter Venus rocks or Venus analog rocks under Venus conditions, so high temperature oxidizing conditions, and see how that alteration affects spectroscopy and how the spectroscopy changes according to that? And can we use that to constrain how all these lava flows are at Iden models? So to do this, Venus surface is 400 degrees, 470 degrees, 92 bars, and a CO2 atmosphere. These are very difficult conditions to replicate in the lab, especially with large enough samples that we can also measure by spectroscopy. So what we've been doing is taking an iterative approach by first only worrying about temperature. So we're going to ramp up the temperature. We're going to do them under Earth's atmosphere, so oxidation, and look at a whole suite of samples. So olivine, alkali basalt, and all sorts of different pyroxenes, and see how quickly these oxidize under terrestrial conditions at 470 degrees. The great thing about these is we can run these experiments as long as we want. We can run them with as large of samples as we want. And so we can measure them by spectroscopy. We can do scanning electron microscopy. We ran them up to 7 weeks. We actually stopped them at 7 weeks because this was my intern's project and her internship was ending. And so that was the timing of stopping that, but we could have run these longer. We did them at 600 degrees. We also did the olivine only experiments at 900 degrees. 900 degrees is not directly relevant to the Venus surface, but tells us what time would do, because temperature speeds up our experiments. And so this is for a longer duration. For the olivines, these were our discarded olivines, and the ones we didn't choose because they have alteration already on them or inclusions. We chose gem quality olivines with as little alteration, with as little inclusions as possible. For the alkali basalt, we literally cut slabs of alkali basalt. We did not on purpose choose things that were fresh. We did measure everything before and after by both SEM and VNIR, including the pyroxenes, and so we have a one-to-one comparison of what's going on in all these samples. We measured this, as I just said, we measured the surfaces before and after. Mineralogy for the olivine, we actually also did Raman. This was part of a master's thesis looking at olivine oxidation on the Earth, actually, in mantle xenoliths. We actually also have magnetic properties of these, so if you're interested in that, go to Knopfler. For the basalts and the pyroxenes, we did SEM and electron microprobe. Texture we got by SEM. For spectroscopy, getting emission like we have for Venus is quite difficult in the lab, but it's a lot easier to measure reflectance. Thankfully, emission is just 1 minus reflectance, and so there is a one-to-one comparison between these. And just for a sort of sanity check, Our experimental approach, I'm going to focus on the olivine and alkali basalts. For the Venus conditions, as you saw, we do have one alkali basalt that's been measured and two tholeiitic basalts, but the chemistry and the mineralogy are not well constrained. So this was our first order sort of comparison. These experiments were done in air, which is FMQ plus 10 approximately. The Venus conditions are at CO2 with sulfur, and the oxidation state is thought to be at or above the hematite-magnetite buffer. So we're talking about our experiments being 5 orders of magnitude more oxidizing and without CO2 and sulfur. There's a reason why this is okay, and we'll come back to that at the end. Our experiments were done at 600 degrees and 900 versus 470 for basaltic plains and 92 bars. 470 versus 600 should not make a large difference, although this will speed things up a little bit. 900 degrees obviously will speed things up, and this was only done for the olivine. We measured the surfaces before and after for spectroscopy, and this is directly relevant. However, we have full spectroscopy, and for Venus right now, we're really only focusing on the 1 micron feature. And so I'll point out where the 1 micron feature is on my graphs. So one other caveat is these measurements were all done at room temperature, whereas emissivity is done at 470 degrees on the surface of Venus. And this is a paper that we published this year with data from, again, those 2 papers by Darby Dyer in 2021 and Halbert in 2021. This is reflectance versus wavelength. The squiggly lines are for granite, sandstone, and anorthosite, dacite, hematite, dunite, and basalt. The squiggly lines are at 25 degrees C, so room temperature. These stars, the squares, all of these symbols are the exact same rocks, but measured at 470 degrees C. And you can see our measurements were done at 900 nanometers or 0.9 microns, and just below that. So we're just below that 1 micron feature that we can see on Venus. And importantly, at least at first order, and with the exception of hematite, first order, we are getting a good match. There are some differences, but we are getting a good match. And this is the same thing that Darby Dyer and Jorn Halbert have shown as well, that there are subtle changes between room temperature and high temperature measurements, but first order, especially for things like basalt down here, reflectance to from room temperature to high temperature is about the same. So that's great. So now getting into the experiments, again, the original experiments were done for the Earth. These are from Knoffel et al. These were republished in my paper last year, applying them to Venus. This is 600 degrees, 900 degrees. This is the unaltered olivine. This is time in hours. So 12 minutes, 1 hour, 5 hours a day, a couple weeks. And then this is a month. You can see for 600 degrees, you can see the olivine starts getting redder. You can see red material starting to form throughout this. And then after a month, it still looks like an olivine. It's still kind of shiny, but there is a red coating or dark coating covering this. For 900 degrees, after 12 minutes, we have that same dark coating. And so this tells us that these experiments nicely should just be at the end of this and keep going, which is perfect. So this is just adding time to our lower temperature experiments. So we're getting a darkening. And then after about a day into about a couple of weeks, we start to see a change from it going from olivine to darkening to a reddish color and much duller red coating forming after a month. So you can see that there's a change in mineralogy with our coating happening through time, where we're producing one mineral and then producing another. And this is the formation of iron oxides. We're first forming magnetite on the surface after a month at 600, and we're forming hematite as we go to longer and longer times of oxidation. We also did, we cut through one of these and did SEM on this. This is the olivine in the interior. This is that oxide coating. I'm sorry, this is the oxide filling cracks. This is oxide inclusion within the olivine itself. And this is olivine, I'm sorry, iron oxide coating the olivine. And the interesting thing, this is an experiment done, this is this one down here, so this is after a month at 900 degrees. And interestingly, when you look at a cross-section, you're still mostly seeing olivine in the interior, though the iron oxides are forming coatings and within the inclusion. However, if you broke the sample open, it's still mostly olivine. When we look at Raman data, so these are our normalized peaks, and these are just spread out this direction so you can see them. These are example of other minerals. So this is quartz, enstatite, clinohumite. This is hematite here. This is olivine untreated down here, the nice olivine doublet. This is 600 degrees. This is 900 degrees. This is 14 and 15. So this is this experiment. And we actually did duplicates through this entire thing. So 15 is the duplicate of the month-long experiment at 900 degrees. You can see the 600-degree experiment still has this nice olivine doublet, though the doublet has shifted with the right peak being higher than the left peak. You can see other peaks starting to form. These are consistent with the formation of iron oxides. For the 900-degree experiment, you can see that, first of all, we've got a lot more noise in our experiment. However, you can still see this nice doublet here. So the Raman is still seeing olivine, but this is hematite, and you can see we are getting the peak here, and this giant peak here. And so it's consistent with the formation of hematite. Interestingly, there's a peak here consistent with quartz. I'm sorry, consistent with enstatite. You can see potential evidence of the doublet here. And so there may be other minerals forming as we go to longer and longer times of experimentation. But the main minerals that are forming are olivine going to iron oxides in this. VNIR spectroscopy tells us a slightly different, although similar story. And this is telling us about the detection limits and the detection capabilities of this. So here's 1 micron. This is unaltered. This is with oxidation. This is the most oxidized. This is more or less a flat line telling us we wouldn't be able to tell that this is olivine, whereas this is nicely beautiful olivine. Going to 900, again, these are offset for oxidation. We've got a beautiful olivine. And after a month at 900 degrees, this is a beautiful and perfect hematite spectra. And so what this is telling us is we're going from olivine to flat spectra, which is consistent with magnetite, going to hematite as we go to more and more oxidation. So if this is applicable to the previous results, that the high 1 micron emissivity modeled for lava flows in the surface of Venus is caused by olivine, our results suggest that these flows are months to years old and volcanically active. However, this is for olivine only, and lava flows are made up of a lot more things. So if we look at the basalt alteration, this is unaltered. This is altered, and now we're 2 months or 7 weeks. And you can see all of this pitted material, and you can see all of these bright dots. These are all iron oxides starting to coat the surface of the basalt. And they're coating olivine and basaltic glass first. And so you can see there's, this was vitrified basaltic glass. You can see a skeletal olivine here, and that's what's being coated in terms of iron oxides here. We did spectroscopy. These are not offset because these tell actually really nice stories. So we've got a very flat, unaltered basalt here, 1 week, 2 weeks, 4 weeks, and 7 weeks. We are getting a brighter and brighter spectrum. We are losing the peaks or the features dedicated to basalt, and we're getting a spectra that looks very much like hematite. So with increasing time, we are going from reflectance at 0.95, I'm sorry, at 5% or emissivity of 0.95 to reflectance of 15 or emissivity of 0.85. And we are losing the features of olivine and gaining the features of hematite. As I said, these are not necessarily the exact conditions of Venus. Thankfully, we are doing those now. So we have a paper in review by a master's student at University of Tennessee, Knoxville, where we did experiments at 92 bars of CO2. There's ongoing experiments adding sulfur to these, but the CO2 bearing experiments match our mineralogy exactly. Iron oxide formation of hematite. This is a TM image showing iron migration to the surface. And again, very similar timescales to our experiments of days to months. So what this is telling us is these high emissivity lava flows. If we can use our spectroscopy as a one-point comparison, will tell us that these are years, decades, at most about 100 years old for the highest emissivity or the lowest reflectance lava flows. And that we can use these to sort of get a first order age date of our lava flows. So as I've shown, Venus is probably volcanically active either today or in the recent geologic past. Veritas, DaVinci Plus, and Envision. It's one of the things all three of our missions are going to be going to look for is evidence either in the atmosphere from chemistry or changes in the surface or these emissivity measurements to look for the evidence for active volcanism. However, as I've shown you, this is probably not a very good cartoon image of Venus volcanism. Instead, we're looking more like this, where we've got our runny lava flows flowing out. This is the most recent eruption in Hawaii. And so some answers, or at least constraints on some of the questions I posed at the beginning. These were the questions. So what is the volatile content of the Venus interior? We don't have great constraints, but possibly some amount of water is needed, and CO2 is likely needed for producing the alkalic volcanism. Is Venus volcanically active today? Probably. The exact aging of today, whether it's hundreds of years or sooner than that, we'll hopefully know when we get missions back there. But volcanism is in the very recent geologic past and may actually even be active today. And with that, I'm happy to take any questions, and thank you for your attention.
Thank you, Justin. Great talk.
Yeah, thank you very much. Yeah. So I do want to take this opportunity to thank Justin once again for a very interesting talk. If people want to stick around and ask questions of Justin, he can probably stick around for another minute or two.